start, everyone. Welcome to this week's Arrive session. And I'm very happy to introduce Matt O'Toole as the presenter this time. Matt very recently joined us 2 weeks ago.
2 weeks ago, yeah.
He worked in computational imaging. Before coming here, he was a postdoc at Stanford, and even before that, he was a Ph.D. student at the University of Toronto. And during this time working in computational imaging, Matt has developed very many very impressive imaging techniques and new kinds of cameras that he will show us a lot about in this talk. So we're all in for a good treat. So I hope you'll enjoy the talk. And go ahead.
Thanks, Yanis. So as a disclaimer, so I gave a talk, I guess, 5 or 6 months ago before getting hired here. And so there's going to be a little bit of overlap for those of you that had attended that talk. But hopefully there's enough new material as well here that will keep everyone interested. And as Yanis pointed out, I work in a space called computational imaging. And the idea here is to try to develop both cameras and displays that can capture or produce visual information in new ways. And the idea involves trying to look at changing the hardware and software of these systems in order to produce all sorts of new forms of visual information. And I'll give you a few examples here. So there are so-called computational cameras that allow us to capture information in new ways. For example, we can produce HDR images. These are called high dynamic range images. Allow us to produce an image that represents the real world with higher fidelity. So we can capture very bright regions of an environment with higher detail at the same time as capturing the shadows and dark regions of a scene, which is really hard to do with a standard photo. Super resolution imaging involves capturing higher resolution spatial content with a low resolution sensor. And light field imaging involves capturing photos that you can actually change the focus settings that produce that photo in post-processing. Meaning that you can capture a photo and I can change the lens settings through digital manipulation of a light field that represents the light rays coming into the lens of a camera. And a lot of the ideas here are also extended towards computational displays. So there are HDR displays that produce visual content with higher fidelity, super resolution displays, and as well as light field displays. Light field displays allow you to see 3D content without the need of special glasses like those that you would wear in a movie theater. And a lot of my work actually happens to lie at the intersection of these two areas. So I like to think about developing both computational cameras and displays in order to analyze environments. The idea here is to use displays or light sources that you can control to send patterns out into a scene, and use sensors and cameras to capture the light that comes back in response in order to try to pull out information about your scene. For example, the shape of materials or what these materials are made of, and so on. Now, one of the most important components of these systems is the sensor. The sensor's role is to convert photons of light into digital information. And there are a lot of different types of sensors out there to do this. Now, the standard sensor that you have on your cell phones is the standard RGB sensor that basically kind of acts like a bucket. It captures a lot of photons of light. It fills up this bucket, and then you read out the value, how full is the bucket after a certain exposure time. And this is one way to capture light, but there are a number of different ways to do this as well. And today, I'm going to talk about imaging techniques that involve a different type of sensor, known as a SPAD. A SPAD is a single photon avalanche diode, and the SPADs operate very differently than the sensors on your smartphone. So a SPAD is able to detect individual photons, one by one. And the way it works is usually you pair one of these SPADs with a picosecond laser. This laser sends out these pulses of light into an environment. That light will interact with the environment in complex ways, and some of that light will eventually reach your sensor. And when a single photon hits your sensor, it triggers an event. A SPAD can detect this event and also measure the time that event took place. This time can be compared to when the last pulse of light was sent into the scene to figure out how long it took for a photon, a single photon, to travel through the scene and onto a sensor. Now, this time value actually presents you with a different form of information that you wouldn't regularly get on your cell phone. Instead of just capturing intensity now, the number of photons, you can measure where or how long it took for light to travel through the scene. And that can give you cues about where objects are relative to your camera, as used in typical time-of-flight sensors. And you can pull out other forms of information as well, as we'll talk about in this talk. Now, one photon of information is not all that useful. You get one photon of information, but really, we want to collect a bunch of photons. So you can repeat this process millions of times a second in order to capture a distribution of photon arrival times. And so what these SPADs produce, basically, are these histograms. This histogram shows a temporal impulse response function. It shows how light can travel through different parts or take different paths through the scene to reach our sensor, and each path might correspond to a different time-of-flight value. And this information provides a new dimension for understanding how light interacts with the scene. Now, here are two different SPAD devices that I'm particularly familiar with. So the one on the left is a single pixel SPAD. And on the right, we have something called a linospad. This is a linear array of SPAD pixels. Now, these SPADs are fairly low resolution right now, but there's a lot of work going into trying to improve this technology to get it to higher resolutions, to make it cheaper, and so on. But these are the two types of SPADs that I'll be talking about today. And we'll look at a number of different applications that make use of these SPADs. And the three that I'd like to focus on involve transient imaging, which is to capture how light interacts with the scene at trillions of frames per second. So you can see the propagation of light through an environment. Single photon 3D imaging, which is the idea of trying to capture shape of an environment when you have very few photons of information to work with. And non-line of sight imaging, which is the idea of trying to image the shape of objects that might be hidden from direct sight. And so you can use objects like walls or other surfaces and turn them into diffuse mirrors in order to see objects that would otherwise be hidden from your camera. So I'll start off with transient imaging. And about 7 years ago, I was introduced to this topic by Ramesh Raskar, who gave a talk here at CMU at ICCP, which was hosted by Srinivas. And I remember this very, very vividly. He showed this video of a Coke bottle and a pulse of light traveling through this Coke bottle. And so there's a pulse of light that will start at the bottom here, and it passes through the Coke bottle, and you can see the propagation of light basically happening. And the light is basically traveling a few millimeters every frame here. And this is an example of a video that was captured essentially at 1 trillion frames per second. It's capturing the physical propagation of light through this environment. You can see light scattering through different parts of the scene. And in fact, I'll turn off the lights here temporarily. Or not. There we go. So you can see this pulse of light. And so you see this big pulse of light, but you also see light scattering in all different directions, right? And this provides a new dimension of information that can be exploited to understand what is this scene actually made of. What does the Coke bottle in this case contain? In this case, it has a little bit of water. Well, it's filled with water, and there's a little bit of milk added to it so that the light scatters as it propagates through the Coke bottle. And there's light that's bouncing around, and that can tell you information about material properties, the shape, objects that might be hidden from view. Now, this is one of the fastest videos that has been produced. And Yanis has built another version of this as well. And I'll talk a little bit about that very, very briefly. But it's also one of the slowest cameras as well. So even though this is capturing basically videos showing the propagation of light, and the videos are recorded basically at 1 trillion frames per second, the actual process to capture this video takes about a day. It involves very, very expensive equipment and requires very, very careful manipulation of the equipment to get everything to line up just right to capture this image or video. So when I joined Stanford a couple of years ago for my postdoc, I started getting involved with these SPADs. And the first thing that we looked at is, well, can we use a SPAD, which is much cheaper, much easier to work with, to capture the same type of information? So here's a regular image showing a fiber optic cable where we attached a light source to one end. And this is a pulsed light source that sends out these pulses of light through the fiber. So this is another transient image. It's not quite as high quality as the previous one, but this video was captured in about a minute. And it produces nearly the same quality image. And you can see all the light traveling through the fiber itself. You can see light scattering in the background. And you're capturing all this information that's very valuable to someone in computational imaging, because you can start analyzing scenes in a different way using this type of information. And as I mentioned, there's a number of different technologies that can capture videos like this, one of which was developed here, or at Harvard, and Yannis brought this system here that involves optical interference to capture even higher resolution videos, slowing down light even further. And that's great, but it tends to be very sensitive to vibrations in the scene. It takes relatively long periods of time to actually acquire that data. The street camera is the first video that I showed you. Again, it's very expensive, and it's very hard to capture the data as well. It takes a long period of time. There are other types of time-of-flight sensors that can do an OK job at capturing these types of images, but SPADs are really the way to go, in my opinion. SPADs are it's an example of a technology that's fairly cheap, relatively speaking, and easy to use so that you can capture this type of information. And the way we did this was actually to use the linospad, an array of SPAD pixels, to capture the light from the scene a little bit quicker. So in this case, instead of just one SPAD pixel, we have an array of these SPAD pixels. And so instead of just capturing one histogram, we capture multiple histograms. Each histogram represents the light that's coming from a different point within the scene. And so the information that we're pulling out of this particular system is a spatial temporal image. On one dimension represents the time it took for light to travel to different points on the sensor. And the other dimension represents space. It's basically imaging a scan line within the scene. And then we built a system around this in order to basically scan the scene with our line sensor, one line at a time. And let's see here. There we go. So we can use that line sensor in order to capture scan lines of the scene and capture that second spatial dimension. And this produces these spatial temporal volumes, which encodes space, which represents two dimensions, and time. And by slicing up this volume along the time axis, we can play back these videos, showing, in this case, the pulse of light traveling through this optical fiber. Now, here's just another example of one of these transient images that we had captured. In this case, we have a statue that's looking at itself in a mirror. And we have a wave of light passing from the right side of this scene to the left. When that wavefront hits the mirror, it actually splits into two directions. Some of that light comes back towards the statue, and then the other wavefront looks or appears to travel through the mirror itself. We're looking at the reflection of light off of the mirror and bouncing around through the scene. Now, that's an example of the raw information that's coming out of some of these SPAD sensors. And we're really interested in pulling out the scene properties from these transient measurements. So one area that we can apply these SPAD sensors is in single photon 3D sensing, where we want to capture the shape of an environment with some of these SPAD sensors. And it's very similar to how existing LiDARs function. So a LiDAR system, or a light detection and ranging system, is often found or paired with self-driving cars, and they're used to capture point clouds representing an environment. And this works basically by sending out these pulses of light in the environment and measuring the time it takes for that light to come back. Now, usually this doesn't involve SPADs. It uses something known as an APD, but it operates on a very similar principle. Now, SPADs, though, have some characteristics that potentially allow for these LiDAR systems to see even further and at higher resolutions and at faster speeds than in existing systems. So for this project, we actually looked at trying to combine LiDAR technologies with these SPAD sensors and develop algorithms to push the state-of-the-art in LiDAR sensing. So again, a LiDAR works basically by using a laser to send a pulse of light into a scene, and a SPAD might output a histogram like this. You might get a few photon counts from that laser, from the light that's coming back off of that object. And the position in time represents how far that object is from your sensor. Now, easy, right? We just need to figure out when the photons came back to capture the shape of that object, or how far the object's from the sensor. But it gets a little bit more complicated because let's say the object's a little bit further back, and let's say now the sun is very, very bright. There's no clouds obscuring the sun. What you'd measure in this case might be something slightly different. Now, here you get a bunch of photon counts. A lot of them are actually due to ambient sunlight, right? The sensor will also trigger from light coming from the sun, as well as from the laser. In the case where the object's too far away, you might only have one photon count representing where the object is. So the problem now becomes trying to figure out which photon actually came from our object and what time that photon actually arrived in order to figure out that object's shape. Now, there are a number of strategies we can use to do this. We can take longer exposure times, or we can try to boost up the power. But there's basically a trade-off between the maximum range of these systems, the acquisition speed, and the resolution of the depth maps or 3D shape point clouds that we're capturing with these systems. So we need to find a way to try to maximize basically all of these parameters. And this involves basically trying to find algorithms that can process the raw SPAD information, the raw histograms that are coming out of our SPAD, and take advantage of certain priors that we might know about our scene. So this was work that started basically in 2012 by a paper titled First Photon Imaging, and it involved trying to capture basically these SPAD measurements where you have very few photons coming back and then trying to process the result. And this involves basically trying to figure out which one of these photons correspond to laser photons, the light coming from our laser, and which ones come from sunlight. And so typically this is done by trying to censor out to ignore or identify which ones are from sunlight and then use the remaining ones, the remaining photon counts due to your laser to figure out depth. But this ends up being a very, very hard problem. And the solutions thus far ended up being very heuristic, trying a number of different things, a number of different strategies to pull out or separate out the ambient light from the laser light in order to get shape. So we tried to tackle this problem in a slightly different way. And you might already know where this is somewhat going, but it involves trying to basically take these SPAD measurements, represented with the spatial temporal volume. And in this case, we also might have intensity information about our scene. And we throw it into a CNN. And the goal is to basically try to get a better depth map out at the other side instead of trying to handcraft priors and algorithms to exploit certain properties about our scene. Why don't we just try to learn that information and get a better depth result by taking advantage of existing CNN architectures? So that's what we did. And this project involved trying to understand the noise characteristics of the sensor, trying to develop architectures around that can exploit or take advantage of that information, and then building a physical prototype to capture that information so that we can do imaging of scenes at somewhat long distances at live video rates. So the SPAD basically produces this histogram, and it's related to the underlying temporal impulse response function shown on the right. So when you measure the scene, you might only capture the light from a number of pulses, right? So you have a finite number of pulses that you can set out into the scene, and you measure a finite number of responses in response. So you would end up getting a very noisy histogram rather than this nice smooth function that's shown on the right. And the measurements that you capture are actually characterized by this image formation model. And I'll just go over this very briefly. Basically, the histograms shown on the left here are basically a sampling of the function on the right. And the samples are drawn from a Poisson distribution. Basically, there's a Poisson distribution of this function where n is the number of lasers, pulses that you're sending out into the scene. You have this underlying temporal impulse response function, which is shown in the right here. Then you have some scalar parameters that describe radial fall-off, reflectivity, maybe the detection efficiency of your sensor, and so on. And on the right, you have these terms that describe how much light might come from your ambient sources as well, which is shown in red here. And the goal is to try to find a way to separate out these two. You're trying to figure out which photons are coming from your ambient sources, which are coming from your laser source. And one way you can try to find the separation between the two is that the laser always concentrates light at a particular point in time. So you always get this peak, and if you can identify where this peak is in time, then that's a good indicator of when that, which photon counts are actually corresponding to the laser that you're sending out into the scene. The remaining photons, which happen to arrive randomly in time, is due to your ambient sources. So the light from your sun will actually trigger your sensor at random times, and that corresponds to this DC offset. So in short, this is the image formation model for the sensor. And so we took a bunch of, in order to train our CNN, we grabbed a data set that corresponded, that had basically intensity images and depth maps, and we used this information to generate simulations of SPAD measurements. And then we would basically take, in the end, those measurements and then try to pull out the position of the pulse that's located within these measurements using that CNN architecture. So on the left, we basically use that image formation model, take that the temporal impulse response function as input that was given by our ground truth depth measurement, generate random photon counts using our image formation model for the SPAD. And then we use a CNN architecture to basically produce or regress this pulse on the right. And we'd use the KL divergence loss to try to minimize the difference between the output of the CNN and the ground truth pulse. And that's how we basically train the data. And then we tried a number of different architectures and tested how well they performed under different circumstances. So one involved basically a three-dimensional convolutional neural network. It involves a number of 3D convolutions done over multiple layers, takes the SPAD measurements as input, and outputs a depth map in the end, where the depth map is generated by taking a max, basically max projection along the time axis. Now this produces basically a point cloud representing the geometry of your scene in the end. And we can also incorporate intensity images within the CNN as well. So this was an example of a second version of this architecture that we tried. And this helps us actually take into account certain, basically the CNN would segment out certain parts of the scene and cluster them together and use information that may be present across multiple SPAD pixels or multiple regions of the scene, and that helps us actually determine depth with more accuracy. And we also incorporated another branch to our CNN that tries to improve the spatial resolution of our depth map. Because our input intensity image has a higher resolution than our SPAD volume, we can combine the two to get a higher resolution depth map in the end as well. So here's a few examples of simulated data sets that we processed. So here we have our transient measurement, basically this spatial temporal volume of SPAD count. So every point within this volume represents a detected photon event. And 2 of these photon events represent the signal from our laser, but 50 are represented by noise, ambient light that was present in the scene. And we're trying to distinguish between the two here. Now on the right is a standard log match filter that's used on the result. I'll just skip ahead. And on the bottom right here is the results that we got out of our CNN. And you'll notice that we do pretty comparable to this work that was done in 2017, Rappin-Goyal, except that Rappin-Goyal involves this heuristic algorithm that tries to process the data. And because of how that algorithm is designed, it cannot easily incorporate intensity images into the algorithm. And with our CNN architecture, it's a lot easier to fuse basically information from intensity images as well as process the images from our SPAD sensor. And the intensity images actually become critical because it helps us fill in regions of the scene that might be really hard to detect. So here you can see that on the left, we're missing basically the depth values along this ring here are kind of missing, whereas our intensity image allows us to preserve that information and fill in that information a lot more easily with our CNN. Here's another example. So in our case, we tried the first version of our architecture, which didn't involve that intensity image. And you can notice that there's a bunch of different parts or artifacts that's present in here. By ignoring the intensity image, it's harder to fill in these regions of the scene with good accuracy. And we perform worse than last year's algorithm that was presented on this subject. But by taking the intensity into account, you actually can push the algorithm even further and do pretty well. So it's possible to get depth out of just the intensity image, but it's very, very hard to do that as well. So there are all sorts of CNN algorithms, but it's possible. So you can, the algorithms that I'm familiar with so far are able to get relative depth, but are not able to figure out the absolute position of that depth, because there's fundamental ambiguity in terms of scale, essentially. Whereas the time of flight or the SPAD measurements allow you to find the absolute position. And this is important, especially if you're trying to deploy some of this technology onto a car. If the car is, you want to know that a car in front of you is 10 meters ahead of you, not 100 meters away. So of course, relying on just a single intensity image may not be the right solution in that case. So we built a system around this. And so this is one of the SPAD systems that we had built. This involves what we call an epi-scan, where we illuminate a line within the scene, and we image light coming back along the same line. And the top part of the system involves our illumination optics, and the bottom part is our imaging optics. And the light coming back actually gets split into two directions. One direction goes into a regular intensity sensor, so we can capture the intensity or the light with a regular high-resolution RGB sensor. And the remaining light goes to our SPAD, which we can use for capturing time-of-flight measurements. And this is what our sensor actually looks like. So right now, it's actually scanning very quickly from left to right. And when it's scanning, it's very hard to see the light, because we're actually using a very low-power light source in this case. So the light here is actually 0.1 milliwatts of average power. And so that's very few photons going out into the scene and coming back. It's a little bit easier to see when we turn off the lights. Here we go. Now the scanning is happening again. The scanning is happening at around 20 hertz. We had some results that were at 5 hertz, some that were at 20. But it's a lot easier to see what's actually going on with the lights off. But when the lights are on, what you get are these measurements that contain both light from our laser and light from the ambient sources within the room. And it gets hard, it becomes challenging to try to separate the two. But that's the goal that's presented in front of us. And so these are the output of our system, captured at 20 hertz in this case. And here are a few different reconstruction algorithms that we've tried. So the bottom three are the 3 different versions of our architecture that we designed for this project, where if you combine the intensity image, you can get basically improved depth resolution, though there's not that big of a difference between the two on the left here. And on the right, by taking advantage of the upscaling architecture, we can actually improve the density of the point cloud that that's being generated with our system.
This is all frame by frame, right?
This is done frame by frame. So every frame is done independently here. So there's a good idea baked in there, where it's to try to take advantage of the fact that there's information across frames as well that you can potentially exploit. So that's another way to further improve these results as well.
Use two-hole filling.
Yeah, exactly. Here's another example. So in this case, we have about 0.85 photons on average coming back to our pixels. So some pixels don't actually receive any light from our laser. And the rest are due to ambient photons that are present within the room. And here's the result. So when you upscale, you also get these floating pixels, which is a bit annoying. So we're still trying to figure out a way to get rid of these artifacts that are presented when you upscale the point clouds. It's basically blurring the depth values between 2 different points in space, which creates these floating points. And here's an example of a result that we captured outdoors. So this is done under indirect sunlight. We couldn't handle direct sunlight right now because we're using a very, very, very low power laser. But here we have an extreme amount of ambient photons that are being presented, even though this was done under indirect sunlight, so in a shaded region outdoors. But despite that, we can still reconstruct the geometry just fine. Now, as I mentioned, basically our system right now it's using very low power laser, and so we can only image about 2 to 3 meters in distance. But the same type of idea has been also used with other systems that can achieve 800 meters range with these SPAD systems. And there's a paper also that's titled 10-kilometer range LiDAR imaging or something like that. So it's pretty incredible how far these systems can actually push your ability to see if you design the system just right. So for our prototype system, we're using a low power laser, which limits our range, but there's no reason why we can extend this to much farther ranges. Now, for the last part of this talk, and probably the topic that interests me the most, is this idea of non-line of sight imaging. So the task here is to try to find ways to capture images of objects that might be hidden from direct line of sight. So just to start off, just to explain what this topic's all about, here's an example. So we built a camera system, which is shown on the right here. And the goal is to image this object that's on the left. And the challenge is that you have an occluder that's in between. There's something that blocks the view of that object. So there's no way for light to travel between the object and the camera system directly. But there are ways to indirectly illuminate and image that object by using surfaces like walls or the floor to indirectly steer light to regions of the scene that might otherwise be hidden. And that allows us to capture images of objects that look like this on the right. And this can be done, in this case, this is done in about 2 minutes, so a 2-minute scan. The reconstructions take less than a second. And we're actually getting this to work at speeds that are much faster. So recently, we've actually developed another version of the system and that is able to operate at 2 hertz. So you can actually start moving objects around and see the shape change over time, even though these objects are hidden from sight. And so it operates very similar to one of these LiDAR systems. So the goal, or the way we do this type of imaging, is by measuring the time it takes for light to travel through a scene and come back to our SPAD sensor. And then we process the result to capture shape. The challenges, or the difference, is that we no longer have direct line of sight access to the objects. So we have to rely on other surfaces to indirectly illuminate and indirectly image the light that's coming back in response. Now, in this case, our SPAD produces histograms that might look like this. So this histogram, again, the x-axis here represents time, the time it took for light to travel through the scene and hit our sensor. And the y-axis represents the number of photons that are being detected. And you get these 2 spikes here. The first spike actually represents the direct light. So here we're capturing, this was actually captured over a long period of time, so there's a lot of signal here, a lot of photons that are accumulated. And the first bounce represents the light that's traveling from our system to a point on the surface of this wall and coming straight back. But a little bit later in time, there's some light that appears at around 4.5 nanoseconds, and that's the result of light traveling a longer distance to this hidden object now and back to the wall before reaching our sensor. And by looking at the time difference between these 2 guys, by looking at the photons that arrive first and the photons that arrive second, the time difference tells you how far this object is now from this point on the wall. So the raw output of a SPAD looks like this. So this is the GUI that comes with one of these SPAD systems, and right now it's just producing this histogram at 10 hertz, something like that. And this histogram is being produced for this scene here on the top right. So what our system is doing is actually illuminating and imaging a point on the wall. And the light coming back directly from the wall appears at time 0. And the light that comes later is due to this sign that David, one of my co-authors, is holding up. And the sign is basically reflecting light back to the wall, and that can be used to detect how far this sign is from this point on the wall. We can track, basically, the position of this exit sign, even though we're not imaging it directly. We're just looking at a point on the wall. And so this is great. But that's not the goal that we're trying to go after. We're trying to capture the shape of the exit sign. So we're interested in reading off the letters on this exit sign and capturing its position in 3D space, not just how far the exit sign is from the wall. And this idea was actually developed, again, from Ramesh Raskar's group in 2012. And the first author for this work was Andreas Photon, who's now at the University of Wisconsin-Madison. And they observed that by imaging and illuminating different points along a wall, you can measure the path lengths between the wall and the object. And it changes as you image different parts of the wall. And this provides you with information that can be used to capture the 3D shape of that object. So that is, instead of just looking at one point, you can now scan maybe multiple points along a wall, capture that information now in another transient image, which represents space and time, and then process the result to capture the shape of this object. And in order to understand how you do that, you need to understand basically how these measurements came about. So this is the image formation model for the measurements that we capture with a system like this. So on the left is this function tau, which represents our 3D measurements. And it takes as input x and y, which represents different points along the wall that we'd be looking at, and t, which represents the time it took for light to travel from different points along the wall to the hidden scene and back again. And this is related to our hidden volume, represented by a function rho. So rho represents basically a 3D space. And for every point within this 3D space, represented by x, y, z, rho outputs the albedo, how much light is reflected by that particular point in 3D space. So this is a 3D volume that encodes basically not just 3D shape, but the albedo of a hidden object. And the hidden scene and the measurements are actually related by this operator here, which is represented or separated by this radiometric term and a geometric term. This describes how light travels from different parts along a wall to an object and back again. So here, R, L, and R represent the amount of light that's lost. One over RL squared and 1 over R squared represents the inverse square law. Basically, how much light is lost when light travels from one part on the wall to the object and then back again. And this delta term represents the relationship between how far light had to travel from a point on the wall to the object and back, and the time it took for light to travel through that hidden scene. And in order to express this as a linear system, which is what we use to actually solve this system, we need to make a few assumptions here. So the assumptions made in this image formation model is that there's no occlusions that are present within the hidden volume. So that means that no 2 points within the hidden volume actually interact with each other. We assume that light scatters isotropically, so we ignore the fact that maybe this is a metallic object, maybe it's a diffuse object. We just assume all objects are essentially diffuse or Lambertian for simplicity. And for the sake of this part of the presentation, we'll assume that the wall is also flat. Now, if we make these assumptions and we express this as the image formation model as follows, we can actually discretize this because it's a linear system. That is, we can discretize our measurements, tau, that's what we capture, discretize the volume that we're trying to reconstruct, and we relate the two by matrix A. So all you need to do to solve this non-line of sight problem is actually solve a linear system. Right? So I give you tau, I give you A, and all you need to do is invert A to recover the hidden image of the scene. Great, right? There's a big problem, though. The problem is that A is typically extremely large. So imagine this. Imagine your measurements are 100 by 100 by 100. So it's a low resolution image, 100 by 100, and you're only measuring photons at 100 different times. Right? And imagine that you're representing the 3D shape of your hidden volume with the same resolution. Now, your matrix A will already contain 1 trillion elements. And you need to invert A, not just store it, but invert A to solve this system. So that's a big problem. But despite that, that's how this was done before. So there have been a couple of different algorithms to solve the non-line-of-sight problem that have been proposed, one of which is called back projection, which involves basically computing the transpose of A. So you're not actually getting the inverse of A, which means that you're only approximating the solution, so you get slightly blurry results. And it takes about 10 minutes to compute. Now, if you want to actually invert A, that's possible as well, but you'd have to spend a lot more time to do that. So maybe on the order of hours, it takes a lot more memory because you have to explicitly store the matrix A. And but it's very slow and cumbersome to basically solve this non-line of sight problem. It's certainly not real time, for example. So we wanted to take a slightly different approach to think about solving this problem. And our idea was to maybe we can express our measurements in a slightly different way. And it turns out that you can express our measurements as being just a blurry version of the hidden scene by making a few tweaks to how we both capture the information with our SPAD sensor and system, and how we process the measurements as well. And these tweaks involve basically two changes. The first is that we explicitly decide to image or confocalize our measurements, which means we illuminate and image the same spot on the wall. And this actually simplifies the image formation model. And there's this computational tweak that we can make where we do a change of variables, which allows us to rewrite the image formation model, which into a form that looks a little bit more complex, but actually has a very nice property. Because now, as opposed to discretizing it and expressing it as a simple linear system, it's even simpler than that. When we discretize this image formation model now is just a convolution operation. It's a convolution between our hidden scene and a blur kernel that we know. It's a blur kernel that describes light transport between a wall and this hidden object. And so as opposed to dealing with these large linear systems like before, we can get away with just solving a 3D deconvolution problem, which can be done much more easily than before. So as opposed to spending 10 minutes or hours trying to process the measurements, we can actually get away with doing this in less than a second. Not only that, we can actually get better reconstruction qualities or reconstruction results because we're not approximating the solution here. We're actually solving this linear system, just doing it in a much more clever way. Yeah?
So how do you know the blur kernel? And is it constant for the objects that you're measuring, or will you have different these kernels for different objects?
It's completely independent of the objects that we're trying to measure. It depends on a number of factors. So it depends on how big of a portion on the wall that we're measuring. Like if you're measuring, say, a half-meter by half-meter patch on the wall, the blur kernel will be slightly different than a meter by a meter patch. But we know that information. We can capture that from direct line of sight measurements. And the blur kernel is then just describing the transport operator between the hidden volume, regardless of what that volume actually contains, and the wall. So we don't actually need to know anything about our hidden scene in order to generate that kernel. And this is what the algorithm actually looks like in the end. So we start with one of these transient measurements, right? Spatial temporal measurements. There's a change of variables that I described very briefly, where that change of variables amounts to basically stretching out these measurements along the time axis. And then you solve a deconvolution problem. So this involves taking these measurements, doing a Fourier transform, doing a division, and then an inverse Fourier transform to get the result. And there's a final stretching operation to basically recover the final 3D shape of your hidden scene. And so we built this system that involves, again, a SPAD sensor here on the right. This is now a single pixel SPAD. And we have a lens that's placed in front. There's a pulsed laser, and they're aligned with a beam splitter. So basically, the laser and the sensor are illuminating and imaging the scene along the same ray. And we steer that ray with a pair of mirrors, Galvo mirrors, that allows us to scan basically a 2D patch along a wall. So our laser sends out these laser pulses out into the scene, and then we measure the light that comes back in response. And then we took one of these systems and we brought it outdoors. In this case, the object here is about 125 centimeters away from the wall. And this is what our sensor basically sees. So it's very, very hard to see here because there's so much ambient light that's present. But our system's actually scanning a laser from left to right, basically scanning a 2D patch along the wall, one point at a time. And what it produces is measurements like this guy. So this is the measurements from the light traveling from our hidden object back to the wall. And if I pause this very quickly, you can see there's some structure here. This is actually due to albedo variations along the wall itself. So if I go back, you can see that the bottom of the wall is a little bit darker than the top. That's captured in these measurements. But this signal is actually due to the hidden object. So light traveling from the wall to the object and coming back again. And processing these measurements in the way that I just described allows us to basically capture the shape of that hidden scene very quickly. So less than a second to do something like this. Now, that was done outdoors where we have less control over our system. It was a little bit harder to calibrate everything just right. Indoors, we can do actually a lot better. Now, one thing that I neglected to mention was that the objects that we're scanning are actually retroreflective. This isn't a hard constraint on our system, but it makes it a lot easier to image these objects because they tend to be a lot brighter to our system. So on the right here is the measurements captured for this retroreflective object. I'll see if my computer boots back up, but I'll wrap things up just because I was on the last few slides there. Now, there are a number of different results that we actually tried this on. And so we did most of our results over longer periods of time, around 6-7 minutes each to capture the measurements. But in recent months, we actually got the system to work at around 2 hertz. So this allows us to capture now measurements of objects that are moving around within a scene. And so we actually built a system, the same version of the system, just tweaking things and building the hardware a little bit better. And we brought it on the road with us to a few conferences, CVPR and SIGGRAPH, and actually showed this off at live rates. Now, the system produces noisier results when you shorten the acquisition time, but you can still make out the shape of the object, where the object is in 3D space, and we're looking to refine the system even more. Again, the laser that we're using in this system was actually very, very low power, similar to the single photon 3D sensor that we had used previously. And so that means that there's very little light that's actually coming back from our hidden object in these cases. One way to improve this system is to actually use higher power lasers. So instead of using a 0.1 milliwatt laser, you can actually boost the power of the laser quite a bit while still being eye safe. So in principle, you should be able to get it up to 5 milliwatts. So that's about 50 times brighter without actually hitting your eye safety limits. And if you were to go to infrared, you can even boost that power by another factor of 40, I believe. So in principle, we can boost the power of the system by a factor of 1,000, and it'd still actually be eye safe so that we can bring it around. Now, one of the limitations of the system is that the results that we did was mostly due to retroreflective objects. So retroreflective objects are much more visible. They're a lot easier to see. But in principle, this also works with diffuse objects. So far, we've captured a few diffuse objects, but this takes about an hour to scan, as opposed to, say, a half a second in our latest version. But by moving, again, to a higher power lasers, we can potentially bring the acquisition period down from an hour down to a few seconds, potentially. And so there's a lot of work that that's going on to try to improve this particular system. And I'm almost back on. So but one of the nice properties of this system is also it's very similar to LiDAR. It's basically almost the exact same hardware and scanning mechanism that's used in existing LiDAR systems today. So another thing that we're looking at is to see whether we can implement the algorithms and this technique to see around corners onto existing LiDAR systems that are already being deployed on the road. So that would potentially allow us to start seeing maybe cars on the road that are not directly visible and can be very useful for self-driving cars in order to avoid situations that you might want to avoid ahead of time by being able to see around corners. Now, there we go. So maybe I'll just skip that slide. But so here's the exit sign that I showed you before. And on the right, we're able to capture, not just the shape of that object, but also the albedo variations along that object. So we can make out the letters as well. And even if there's 2 objects present in the scene, we're capturing a 3D volume. So you can not only make out the object that's in front, the S here, but you can make out the shape of the object that's in the back as well. And as I mentioned, this also works for diffuse objects. Now, for diffuse objects, you need to scan over a longer period of time, on the order of an hour, with a low power laser in this case. So if you had a brighter laser, you can potentially bring this down to a few seconds, but we're able to capture the shape of that object nevertheless. Now, I should mention very quickly here that there are a number of different algorithms that can be used to process these measurements. The top two on the right actually were the original algorithms presented for non-line of sight imaging using these time-resolved sensors. And they didn't perform very well, in part because it's only solving an approximation to the linear system that I had presented before. It takes also around 10 minutes to produce. Whereas our LCT algorithm, the basic algorithm that I mentioned, produces this in less than a second. And on our GPU, it's actually a few milliseconds. And you can also incorporate that algorithm into an iterative optimization procedure that can take advantage of priors that you might know about your scene, such as smoothness priors, non-negativity priors, and things like that. And as I mentioned, we built this system and brought it on the road with us. So here's one of my co-authors, David, who is talking about this system as well at CVPR. And it allows us to produce measurements like this. So our system here is on the right. We're imaging this object on the left, and the reconstructions are being shown on this monitor. This is all happening at 2 Hertz. But all of this goes back to basically being able to image single photons and being able to detect the time of arrival for those individual photons. Because these SPADs are very precise in their time-stamping mechanism, we can get really high resolution in terms of the time of arrival for those individual photons, which is what enables our ability to see around corners. Because we really need high resolution time of flight detection for non-line of sight imaging. SPADs are also able to detect individual photons, which is very useful for imaging the shape of objects when there's very few photons coming back. So whereas a normal sensor would not be able to see those photons because it would be drowned out in noise, these SPADs can detect those photons. It's a matter of just figuring out which one of those photons are due to your laser and which ones are due to ambient sources. And there are a lot of potential for SPADs as well as they become a little bit more accessible, a little bit cheaper, a little bit higher resolution. I believe that some of these SPAD sensors can be used for all sorts of applications. And it's a really exciting sensing modality that is very different from existing sensors and requires a whole new way to think about imaging and new types of algorithms to process the results coming from these sensors. So I just want to end off with thanking some of my co-authors. So Gordon, who is a professor at Stanford, and David, who's a PhD student. I worked with both of these very closely on all of these projects. And the sensors, or at least the LinoSPAD that was provided to us, was given by Eduardo, Samuel, and Pierre-Yves. This LinoSPAD enabled us to start working on these ideas, and then it's basically the foundation for these projects. And I also want to thank Kai Zhang, who is a PhD student at Stanford as well. He recently graduated. He's off at Microsoft right now, who actually develops these SPADs from scratch and told us all about the intricate little details that I glossed over very briefly in this talk. But there's lots of interesting details with respect to these SPADs. And if anyone's interested in talking about this offline, I'd be happy to chat some more. Thank you.
Thanks a lot, Matt. We have 5 minutes for questions, so.
Yep.
Could you tell how you simulate the SPAD measurements for NYUT data?
One more time?
Could you explain how you simulated the SPAD measurements in your CVPR?
Yeah. So are you talking about the second project with the 3D shape? Okay, so that was work that was published at SIGGRAPH. And the SPADs is due to a stochastic process. So we take as input basically a ground truth temporal impulse response. And this is basically a probability distribution for when photons are going to arrive at your sensor. So basically, you just need to sample this randomly according to some distribution in order to generate your events. So it's basically just that's your probability distribution function that is used for generating your signal. Yeah?
So, how do you know like your time, even if your samples are public from distribution? What if we have like a larger environment and we're trying to emit things that are like much farther away? How would that look like in terms of?
So if it were a larger environment, the pulse might appear somewhere else in time. right? So if you're imaging something that's further away, the pulse would appear later in time. If it were a more complex environment where you have refractive materials or reflective materials,
You have like multiple objects along the way.
yeah. So if you're imaging, say, through a window, there might be light that's reflecting off the window and some light that might go through the window and come back. In that case, it gets really complicated because now you get multiple pulses coming up. And so what is the right way to capture shape in that case? Are you trying to look for the object that's through the window, or are you looking for the shape of the window itself? In this case, we assume that objects are opaque, so we don't deal with that kind of situation. And we assume that there's no what we call indirect light, light that's scattering around. We assume that it's a simple combination between just a pulse like this and a DC component representing our ambient light. But if you want to deal with the more complex situations, that information's baked in the measurements. It's just a matter of trying to understand how to pull those details out.
But this is assuming that we know what we're looking at. Like, what if we were just capturing?
So we don't know what we're looking at necessarily. We know we're making some assumptions about our scene. We're assuming that the scene is opaque. We generally assume that the scene is diffuse, but we don't know the shape, and we don't know the albedo, and we don't know the ambient contribution of light within the scene. So those are the factors that we're trying to pull out from this information. Yep?
Is it possible to exploit what the Kinect 2 is doing, which is use multiple frequencies and then use the phase difference?
Right, so Kinect is another example of a time-of-flight sensor, and it operates on a very different principle. So in that case, as opposed to sending out pulses of light, the Kinect sends out these basically intensely modulated signals at different frequencies. So it's definitely possible to use intensely modulated light sources in combination with SPADs, and that might offer you some different type of information that you can exploit in a different way. This is something that I haven't looked at, though. Yeah. Sorry, are you talking about this?
I think just the images, few slides back, I guess.
Here?
Yeah, so the zoomed in version of.
Oh, yeah, before that.
Yes.
Yep.
So here in the left, like before it magnification, you can like clearly see the contours.
Yeah. So you said that, so the contour so in both cases, there's a big depth discontinuity here between the face and the background, right? And that's captured pretty accurately in both cases.
Yeah.
Right.
So within the blue region, I'm talking about.
I see. So it is a little bit smoother here.
Yeah.
And that's because of the priors that are being used in this particular method. So it enforces, I mean, one of the challenges with this method is that there are a number of different parameters you have to kind of tune to get the thing to work just right. And one of the parameters is, well, let's make this smooth. So it might look better in some ways, but it might not actually be better. And in this case, if you're to compare these results to the actual ground truth depth map, this works better than the one on the left. Yep.
So if you looked at two different materials, would the time it takes for a photon to get back be different?
Well, it depends. So if both materials are opaque, they'll both send light back at the same time. Now, if you have something like skin, which is translucent, light might actually penetrate skin, bounce around, and then come back at a later point in time. Now, we, again, ignore all that, but that's useful information. So you can figure out basically what parts of the scene are due to translucent materials by looking at how translucent materials manipulate the temporal impulse response, that time of flight values that you're capturing. And you can use that to maybe classify what are you looking at, whether you're looking at a person made of skin versus an opaque object.
So, I mean, is it possible to determine what kind of material? Because I'm just imagining, like, you have some objects on a table,
yeah.
and maybe you have a camera, and you're going to try to see how far away they are so you can pick them up. Depending on the type of material, right, you might think that something is in one place, but actually it's a little further away because you didn't know what the material was or something like that.
That's right. So there's definitely been works on using these types of measurements, time of flight measurements more generally, not necessarily just with SPADs, with Kinect sensors as well, in order to classify materials so that you can potentially figure out what those materials are made of and maybe even capture the geometry of those materials with a little bit more accuracy too.
You can even use the measurements to not just classify the material, but figure out optical properties. Like say this is so dense, this is dense, that kind of scattering function and so on.
And you can potentially use the light that's reflecting off the materials to different parts of the scene to start capturing reflectance functions too.
Yes.
So there's all sorts of things that you can start pulling out from the way light interacts with the scene. And time of flight measurements give you one additional dimension for doing this type of analysis. Yep.
Could you please elaborate more on the priors which are used for non-line of sight imaging?
Right. So I briefly mentioned that there are a couple. Let's see here. So there's this result here on the bottom right that made use of certain priors. And the result on the right involves an iterative scheme that takes a little bit longer than the results on the left. Now in this case, the signal is so strong that the results are pretty similar. But when using a diffuse object, the signal might be a lot weaker, where it's much more important to take advantage of those priors. The priors in our case include basically three different priors. Priors on the sensor noise associated with the SPAD. So we know the noise characteristics of our sensor, so we can try to make sure that we're taking advantage of that. So we know how to model the noise from our sensor. We also know the fact that the volume that we're trying to reconstruct is going to be non-negative. So it has to only contain positive values. So there's a non-negative constraint here as well. And there's also smoothness priors that we can start exploiting, as well as sparsity priors, because we're only going to be imaging the surface of objects, not the full, dense 3D object itself. And so these priors can be used to help us reconstruct these images, even though you have very few photons coming back.
So the sparsity priors can be like, suppose you have an estimate of where the object will be, and then so you know an approximate like density of the object, that the object might be present here, so and there might be nothing present around it. Is it like that?
So in this case, this is a 3D volume, but you're only getting a surface within the 3D volume. And the surface is just the surface of the object, because light's not going to penetrate the object in this case. The object is assumed to be opaque.
Okay.
And so because of that, it's going to be sparse along the depth dimension, for example. Okay. So that's something that you can exploit when reconstructing these images.
All right. So we are running over time, so let's thank Matt once again.